Hey gang, today we're going to be taking a look at something called the real number system. So some definitions you need to know. Real numbers are all numbers that exist. So negative 2.5 is a real number. 30 over 7 is a real number. The square root of 30 is a real number. 1.28673521 is a real number. Pi is a real number. Any number you can think of is what we consider a real number and belongs to that set. Rational numbers, we use Q to abbreviate, and those are numbers that can be written as a ratio. So anything that you can turn into a fraction. So, for example, a whole number like 15 is rational because you can turn it into a fraction, 15 over 1. For example, the square root of 36 is rational because you can turn that into 6, which is 6 over 1, and so on. So if you can write it as a fraction, it is rational. Irrational numbers are numbers that can not be written as a ratio. Those are non-repeating, non-terminating decimals. And the most famous irrational number is pi, and that's that non-repeating, non-terminating decimal that goes on and on forever. We know it as 3.14159 dot dot dot. So that's irrational. And also very common irrational numbers are square roots of non-perfect squares. So 36 is a perfect square because when you take its square root, you get 6, which is an actual number. It's not a decimal that you can't turn into a fraction. But if you take, for example, the square root of 30 and put it into your calculator, second square root 30, we get 5.4772255575, which has no pattern. And if our calculator was bigger, that number would keep on going and going and going. And if I try to turn it into a fraction, it doesn't allow me to. So that would be irrational as well as any other non-perfect squares like square root of 5, square root of 3, square root of 17, anything that you can't actually take the square root of. Whole numbers, we know very well. That's the set of natural numbers, which I didn't list here because those natural numbers are numbers that you count and zero. So it's 0, 1, 2, 3. I think everybody knows what a whole number is. I don't know that you need an extra definition for that. Integers are z, and that's the set of whole numbers and their opposites. And you should also know that knows integers from the past. What a lot of kids confuse though with integers is they think that things with decimals and a negative sign are also integers, and they are not. So integers are only whole numbers and their opposite. So something like negative 2.5 is not an integer because it has that 0.5, but it is a rational number because I can take negative 2.5 and write it as negative 5 halves. So it's a fraction or a ratio. So down on the bottom, we have when the square root of a number results in a whole number, it is rational. If the square root of a number cannot be written as a fraction, it is irrational, which is what I explained up top there. Okay, so here's a little graphic organizer to help you figure out what sets any number belongs to. So we have real numbers as the main category. It is the set that contains every number. And that's split into two separate categories, irrational and rational. Irrational is alone by itself. It doesn't have any subcategories in it. If a number is irrational, it doesn't belong to any other sets. And then within the rational numbers, we have integers, and within the integers, we have whole numbers. So we can use this graphic organizer to figure out what set something belongs to. So if something is a whole number, it's also an integer, it's also a rational number, it's also a real number. If something is an integer, it's also rational and also real. If something is just rational, it is also real. And if something is irrational, it is also real. So let's take a look at some numbers and see if we can figure out what categories they belong in. So starting with negative 6, I know negative 6 is a opposite of a whole number, so it is an integer. And since it's an integer, it is also rational and real. Then we have 8 and 2/5. Now right away, I see a fraction there that cannot be expressed as a whole number, so that is rational. And since it's rational, it is also real. Then we have pi, which we talked about before. That is a non-repeating, non-terminating decimal, so it is irrational and also real. Then we have square root of 2, which we talked about before. And let me just show you. If I do the square root of 2 on my calculator, I get 1.414213562. And if I try to turn it into a fraction, it doesn't allow me to. So this is also irrational and real. That part of the board does not want to be written on. Okay, then underneath we have 5.3 repeating. Now, 5.3 repeating is a number that can be turned into a fraction, and hopefully you guys all know that 0.3 repeating is a third. So since it's 5 and a third, it is rational and real. And you should know that anything that is repeating can be expressed as a decimal. I think if we put it in the calculator that way, let's see, if we put in 0.333333333 and keep on going, it may turn it into a fraction for us. Let's see. Look at that, it does. So you can always test it out with your calculator to make sure it's rational. If it turns into a fraction, then obviously it's rational. If it doesn't, then it's obviously irrational. Then 0.05 is a decimal that again can be turned into a fraction. That's 5/100ths. So again, it's rational and real. Negative 2.6 is negative 2 6/10, which a lot of kids, like I said earlier, would confuse this with being an integer. But since it's got a fraction piece to it that cannot be turned into a whole number, then it's just rational and real. And number 8 is repeating, so it should be rational, but again, we can check it. So it would be 8.1212121212121212. I'm going to go all the way through the screen and then press math fraction, see what happens. And it turns it into a fraction for me. I know that it's 8 and 12/99ths because there is a rule that if you divide repeating number by the same number of nines that are repeating, you get that decimal. So for example, that 1/3 that we saw before way over here is actually 1/3 is 3/9. 3/9 simplifies to 1/3. So that's why it's repeating. So 12/99 is the same thing as 0.12 repeating. So anything over 9 is going to make it repeat. If you have one digit repeating, you put it over 1 9, two digits repeating over 2 9s, three digits repeating over 3 9s, and so on. So just something to think about, help you out in the future. So this is also rational and real. Okay, so using this idea, you are going to try some examples on your own. Check in with me so I can make sure you've got it before moving on to the next part of the lesson. Okay, so in algebra, we often refer to number sets to describe a set of numbers that best represent a function. Another way to refer to x values or input of a function is to say the domain. And we've actually seen this show up in a couple lessons, but I didn't really address the actual definition of it because it was in relationship to like an inequality which had x in the middle. So whenever you're saying domain, you're referring to the x values. Another way to refer to the y values or output of a function is to say range. Okay, so domain is always referring to X, range is always referring to Y. It is both vocabulary terms that we're going to continue to use throughout the school year and you should be really familiar with come time for the regions. So given each of the following functions, complete the given tables and state what number set best describes the domain and range of the function. So a family plan for cell phones costs $14.50 per line and $100 for unlimited data. So I can come up with an equation for this right away. It's $14.50 per line plus $100 for unlimited data. Right away, I know this is a linear function. That's something you should also be able to recognize right away. I can go to my table, pull up that function, second graph, and pull up the table that matches it. So I see that for 2 lines, it's going to cost me $129. For 3 lines, it's going to cost $143.50. For 4 lines, it's going to cost $158. And for 5 lines, it's going to cost $172.50. So now we're going to use that to answer the questions about the domain and the range. So again, the domain in this case is the number of lines and the range is the cost. So what number set best represents the number of lines? Well, you can only have a whole amount of lines. So the best number set that represents that would be whole. So you want the smallest possible number set that would represent that. And sometimes on the regions, they will say non-negative integers to represent whole numbers. So that's something you should just keep in mind. Non-negative means just the regular positive whole numbers. Okay, then what number set best describes cost? Well, when we're looking at the cost, we don't always have a whole number. We have parts or numbers that have a half in it. So we cannot say that it would be whole numbers, nor can we say it would be integers. We'd have to go with rational because they are going to have fractions of a dollar as part of the cost. So again, when you're talking about the set that best describes it, you want the smallest number set that the domain and range fall in. All right, so again, you're going to be on your own taking a look at 18 and 19, check in with me before going on to your exit ticket and your homework.